All right, hey AP Chemists. This is our summer work important information part 3. This is, I believe, our 6th lecture. Hopefully get the numbers down. I'll have it labeled correctly. This is going to be percent composition, and I made a note here. This is part of Unit 1 in the school year, so I'm going to skip this in September. We're going to get to this in our notes, and I'm going to say C, summer work. So I could always repost this video so you could do this or see this, but make sure you know how to calculate a percent composition, and this comes and stems from our molar masses. So a big remembering from your math classes is, and this could be from middle school or I don't know when you learn percentages in high school or if you do them, but percentages are you take your part, you divide by your whole, multiply by 100, and that's going to be your percentage. So if I had like 50 marbles and 25 of the marbles are red, 25 divided by 50. So 25 is the part, 50 is the whole, times 100, that's 50%. Going to be similar for compounds, except the whole is the molar mass, right? So for compounds, our whole is the molar mass, and the part is going to be the mass of the element. And so I have that written down here too. So mass percent composition or mass percent of an element is that element's percentage of the compound's total mass. So mass percent of element X in the compound is the mass of element X in 1 mole of the compound, however many there are, divided by the mass of 1 mole of that compound times 100, and that's going to be my percentage. And I actually did an example here. So suppose, for example, we want to calculate the mass percent composition of Cl in chlorofluorocarbon. That's typically found in your refrigerators. CCl2F2. Notice how there's 2 Cls. The molar mass I already gave you is 120.91. That's our bottom number, our whole. The mass percent of chlorine is given by mass percent is 2 times the chlorines, because there's 2 chlorines in this compound, divided by 120.91. That's the whole, the molar mass of the compound, times 100. And so on the periodic table, the molar mass of Cl is 35.45. So I do 2 times 35.45, and that's 70.9. I divide it by 120.91 times 100, and I get 58.64% chlorine. What this means is if I had a 100-gram sample of CCl2F2, 58.64% or 58.64 grams are chlorine. So keep that in mind, that we could use percentages as conversion factors later. If I know my percent of each element, that percentage will always be constant. Percentage will always be constant for a given compound. And this is from, I believe, our part 2 important information. This is the law of definite proportions. Law of definite proportions. We did this. You had a question about hydrogen and oxygen. So I'm bringing this back here. These percentages will always be constant for a given compound. Can they change? Yeah, but then it'll be a completely different compound. If I have CH2Cl2, I will have 58.64% chlorine and then respective percentages of carbon and hydrogen. Let's do another example. Calculate the mass percent of Cl in Freon, a CFC refrigerant. So another similar chlorofluorocarbon. This is C2Cl4F2, and the molar mass is 203.82. I try and simplify some of your calculations by giving you the molar mass, and the AP exam most likely will do that, but we just learned a couple of lectures ago how to calculate a molar mass, so you should double check and make sure you know how to do that. All right, so if I want my percentage of chlorine, I'm going to need my mass of chlorine over the mass of the compound, or that molar mass of the compound, and then multiply by 100 simply. Well, my mass of chlorine, there are 4 chlorines. So it's going to be 4 times my masses of chlorine from the periodic table divided by the molar mass, which is 203.82 grams, times 100. I'll do the math over here. 4 times 35.45 over 203.82. That's going to be, I actually just did the answer. So 4 times Excuse me. Ooh. So sorry, I'm trying to get my calculator working. So 4 times, gives you a chance to copy down, 4 times 35.45. That's 141.80 divided by 203.82. If I multiply by 100, I will get the percentage of 69.57% chlorine. Okay? So, keep that in mind. It's a different compound. It has a different percentage of chlorine. So these two will not be the same compounds, and they are not. All right, let's do another example from beginning to end. So it says calculate the percent composition of magnesium sulfate. I didn't give you the formula for that, but I'm going to remind you from our previous lectures in this part. Magnesium is Mg, sulfate is SO4 2-. Sulfate's a polyatomic ion. That means I'm dealing with ions. Mg is 2+. If I do the crisscross method, I end up with Mg2, SO4 2. But remember, ionic compounds, this is ionic compounds, they need to be expressed in empirical simplified form. So this 2 and 2, I could divide both of them, and I just end up with 1 MgSO4. Another way of looking at this is the cationic charges need to equal the anionic charges, meaning the positive charges need to equal the negative charges. +2 and -2 already equals to each other, but an opposite. +2 and -2 is 0, so I only need one of each. This is magnesium sulfate. In magnesium sulfate, there is 1 magnesium, 1 sulfur, 4 oxygens. Now I could begin to calculate my percent composition. If I want to calculate the percent composition, I need the percentage of magnesium, percentage of sulfur, percentage of oxygen. If I just ask you to calculate the percent composition of the compound, I want the percentage of each element. But look at the previous questions. This one just said, calculate the mass percent of chlorine. Well, I don't care about each element. I only cared about chlorine. If I don't specify the element, then I want all of the elements. So I'll just do magnesium's complete shown out work here, and then we'll do sulfur and oxygen. So I need the mass of magnesium divided by the mass of the compound, the molar mass of the compound, times 100. That'll be 24.3 divided by 120.37 times 100. Sorry, that's getting cut off there. And I get 20.2%. So I have 20.2% magnesium. I'm just going to simplify and do sulfur and oxygen. Sulfur, there's only 1 sulfur. There was only 1 magnesium. There's going to be 1 sulfur. The molar mass of sulfur, if you look on the periodic table, is 32.06 grams of sulfur divided by 120.37. If I times that by 100, I get 26.64% sulfur. And then oxygen, there are 4 oxygens. 4 times 16 is 64 grams oxygen. So 64 grams oxygen divided by 120.37 grams of the compound times 100, I get 53.17% oxygen. If you can't see that, I'll zoom in right here, and I could try and highlight the answers. I got 20.2% magnesium, 26.64% sulfur, 53.17% oxygen. And guess what? What do all 3 of these add up to? 53.17 plus 26.64 plus 20.20. You should get about 100%. The sum of all of the percentages add up to 100%. Something that you might need to remember from a previous math class. These percent compositions can be used as conversion factors. I could say percentages, I could say grams. If I had 100 grams of magnesium sulfate, I would have 20.2 grams of magnesium, I'd have 26.64 grams of sulfur, and I'd have 53.17 grams of oxygen. And you could check the math here and you get the same percentages. And I could use that as a conversion factor. I could say for every 20.2 grams of magnesium, there's 100 grams of my magnesium sulfate. And so if I knew how many grams of magnesium sulfate I have, I could figure out how many grams of magnesium I have, kind of like its percentage. You can also calculate percent composition from given data, right? If I give you data, don't forget that the sum of all the percentages equals to 100%. And then don't forget from our very beginning in our chapter 1 and chapter 2 lectures there, conservation of matter. A 5-gram sample of calcium chloride, that 5 grams has calcium and chlorine in it. It contains 1.805 grams of calcium, Ca. Well, if I have a 5-gram sample and 1.805 grams is calcium, the difference is going to have to be chlorine. What is the percent composition of each element? Well, remember what I said here. The mass of chlorine is going to be the mass of CaCl2 minus the mass of calcium. Why? Right here, calcium plus chlorine is my calcium chloride, CaCl2. So if I want my mass of chlorine, and I'm doing this math separately, because if I want percentages, I need masses of each element. My mass percent of element is the mass of the element divided by the mass of the compound. So mass of CaCl2 is 5 grams minus the mass of calcium, which is 1.805 grams calcium chloride. If I do this math, I will end up with my mass of chlorine, which is 3.195 grams of chlorine. Now I have my mass of chlorine, I have my mass of calcium. I could do my math here. Percentage of calcium is going to be 1.805 grams of calcium divided by the 5 grams of calcium chloride sample times 100, and I get 36.1% calcium. Now I could do all of the math and get the percentage of chlorine, or remember that the sum of all the percentages adds up to 100%. There's only calcium and chlorine in this compound. So if calcium is 36.1%, that means I must have 63.9% chlorine. These two add up to 100. But I'll prove that with the math here. Percentage of chlorine is 3.195 grams of chlorine over the 5 grams of calcium chloride times 100, and you wouldn't believe it, it is 63.9%. So you could also calculate percent composition if I give you data. If I give you the data, use the data. And if there were questions in which you didn't use the data, and they were accurate questions, like when somebody didn't make them up randomly, the percent from given data should also match the percent from the molar mass data. So just keep that in mind. But if you're given data, use the data. I believe I said that somewhere, but I will say, given data, use the data. I gave you 5 grams of sample of CaCl2, and you had 1.805 grams of calcium. I had to use those numbers. All right. So to end here, I'm going to do a sample question that's kind of related to AP Chemistry, but this is great for our basics quiz. And then you're going to be responsible for turning in exercises 16 and 17 and trying the AP style questions. I did have a little bit notes here. If you want, you can actually stop the video here and try and do the sample question and then do the exercises and then come back. So I'm done with the lecture here. Otherwise, I'm just going to do more examples here for you to get more practice with. So if you want to end, you can end, and then you're going to try and do the exercises 16 and 17. All right, if you're still here, I have sample questions related to AP Chemistry. So it says, what mass of hydrogen in grams is contained in 1 gallon of water? And I told you that the density of water is 1 gram per milliliter. So 1 gram of H2O is 1 milliliter of H2O. That's a conversion factor. And 1 gallon, I have 3.785 liters is 1 gallon. Something I didn't give you is that there are 1,000 milliliters in 1 liter. There's a lot of work here. I also did a little bit of work on the side here based off of this set of notes here. Water is H2O. Its molar mass is 18 grams per mole. I want how much hydrogen is in this compound of water. For every 2 grams of hydrogen, there are 18 grams of H2O, and of course 16 grams oxygen. This is kind of like our percent composition here. I could use it as a conversion factor. I could use this, or if I were to convert that percentages, I would say 2 grams divided by 18, so 2 divided by 18, that's 11%. So I could say 11.1 grams of hydrogen for every 100 grams of H2O. It's the same thing. Prove that to yourself. So I'm going to show you how I'm going to use this conversion here, this percent composition, or this composition of elements in a compound, to answer an AP style question like this. And this is great for the basics quiz. So I love to use dimensional analysis. So I have 1 gallon of H2O. Well, I have a conversion factor that has gallon in it, so I'm probably going to want to use that first. If I start with gallon, gallon goes on the bottom. Liters is going to go on top. 3.785 liters is 1 gallon. And so now that means I have 3.785 liters of H2O. Well, the only other conversion factor, because this isn't giving me grams of hydrogen, I'm still at H2O. The only other conversion factor I could go with now, I'm going to use a different color, is this one that has liters in it. I'm going to convert these liters to milliliters so I could start getting somewhere with grams. So I'll take this and say if I have liters, liters goes on the bottom, milliliters goes on top. There are 1,000 milliliters in 1 liter. And if I do that, I'll get 3,785 milliliters of H2O. That's great. So now this is going to help me get to grams, because eventually I need the grams of hydrogen. So I'll use my next conversion factor. I have 3,785 milliliters of H2O. If I start with milliliters, milliliters of H2O goes on the bottom. Grams of H2O is going to go on the top. And this is nice because the density of water, density relates mass to volume. For every 1 gram of H2O, that's 1 milliliter. So it's the same number, 3,785 grams of H2O. I want grams of hydrogen. Well, I'm going to use one more color here, purple. What's very nice is I have this beautiful conversion factor. For every 18 grams of H2O, there are 2 grams of hydrogen. So I'm going to use this in my conversion factor here. 2 grams of hydrogen for every 18 grams of H2O. And this is going to land me at my correct answer of 423.92 grams of H. 423.92 grams. Nice. Okay. There are other ways that you could solve this, but I wanted to do it within the scope of percent composition. I knew the molar mass of water was 18. Prove to yourself that. And then there are 2 hydrogens in there. Each hydrogen is 1 gram. 1 hydrogen is 1 gram per mole. If I have 2 hydrogens, that'd be 2 grams and 18 grams, and I could use that right here. All right. For exercise 16, I want you to calculate the mass composition of just nitrogen in the compound. You're going to have to calculate the molar mass of each compound. I did B for you here. If you look at what I did for B here, first I got the molar mass of NO2, which is nitrogen dioxide. Don't forget how to name these. Nitrogen dioxide. These are 2 nonmetals. So this is molecular or covalent from our previous lectures. There's 1 nitrogen, so I multiplied 1 times the molar mass of nitrogen. There are 2 oxygens, so I did 2 times the molar mass of oxygen. Add those all together. Here is the molar mass of NO2. If I want the percentage of nitrogen, it's going to be my mass of nitrogen divided by this mass of the NO2 times 100, and I get 30.45% nitrogen. If I wanted the percentage of oxygen, I could subtract that from 100 and get about 69.55%. 69.55% oxygen, because the sum of the percentages adds up to 100, but it wasn't asked of you. For question 17, I gave you 3 different compounds, and I just want calculate the mass of sodium in 8.5 grams of each sodium-containing food additive. Whew, a lot of work here. All right, so you're going to have to get the percentages, and then you can get some sort of ratio conversion factor. And then you could use that to figure out what mass of the 8.5 is sodium. So I'm going to do that for letter D here. I kind of started getting us set up, but I wanted to wait. So I have this sodium hydrogen citrate. Its molar mass is 263.11. There are 2 sodiums in here. So if I want the percentage of sodium first, you're going to have to get the percentage first and then use that to get the amount of sodium. I need 2 times Na divided by 263.11 times 100. That's going to be my percentage of Na. So I'll do 2 times the 22.99 divided by 263.11 grams. Times 100. You could check my math. I'm going to do the math right here. 2 times 22.99. Oh my goodness, sorry. 1121. All right, so 2 times 22.99. If I divide that by 263.11 and then multiply by 100, I get about 17.5% sodium. And now what this means is for every 100 grams of this Na2C6H6O7, there are 17.5 grams of Na. I could use this as a conversion factor. So if I have 8.5 grams of the Na2C6H6O7, I could multiply by this conversion factor. I'll put my grams of Na2C6H6O7, grams of Na, because that's what I want. 17.5 grams over 100. I could do this math. 8.5 times 17.5 divided by 100. That means I'll have 1.49 grams of sodium in the 8.5 grams. This is where you're going to use the percentage as a conversion factor. And that's what I did up in the previous page here, right here. That's why I showed that work there. And then finally, this is not required, but this is good AP style questions here. And I want you to think about it. It says a student has a 1 gram sample of each of the following compounds. This is from an actual AP exam. I believe this is the 2016 AP exam, and this one's the 2018 AP exam for AP chemistry. So it says a student has a 1 gram sample of each of the following compounds, NaCl, KBr, KCl. Which of the following lists the samples in order of increasing number of moles? Couple things here. This is where AP comes in. AP connects these topics that you learned and mishmashes them together. So this is why we do the summer work, because then we can start getting to these tough AP questions using knowledge that you have. So something to note, smaller the molar mass, the larger the percentage, larger the moles you'll have. Why? Just a shortcut here, grams divided by molar mass is moles. If I divide by a smaller molar mass, I'm going to get a larger number. If I divide by a bigger molar mass, I'll get a smaller number, or a smaller number of moles. So I have to look at these compounds and think about which of these has the largest molar mass. Whichever one has the largest molar mass will have the smallest moles. Whichever of these has the smallest molar mass will have the largest moles. I want you to convince yourself that the correct answer is D. So you can do the calculations, get the molar mass of all of these, divide each of them by 1, you'll see which one has the largest moles. In a very similar method here, this one already gave you the molar masses. It says, according to the information in the table below, sorry, that's a little typo here, a 1 gram sample of which of the following contains the greatest mass of oxygen. Same idea. 1 gram sample divided by molar mass of sample is moles. The smaller the molar mass, the larger the moles, the larger the percentage. The correct answer is MgO. Why don't you try and answer which would have the smallest moles? thinking about opposites here. Alrighty, and that ends our lecture. You did not have to watch this far. This end of the lecture was just helping you do sample problems. If you have any further questions or concerns, reach out to me in the Remind or email me for help.